All right, so the acids produce H plus in a solution. And then, of course, the bases produce OH minus. And then, of course, when you bring them together, they produce water. An acid and a base, OH minus plus hydrogen, produce water. So let's take a look at some examples. So an acid, for example, would be HCl, aqueous. So the H plus is going to come off as an ion, which makes it aqueous because it's going to dissociate, plus the Cl minus. So this is going to be considered to be an Arrhenius acid because it produces hydrogen ions. There it is, really simple. So let's look for a base. Sodium hydroxide, and you can already see how this is going to work. We get sodium plus the hydroxide, and there it is. So this is now an Arrhenius base. And so what happens is, if you were to put these together, right, if you were to react them together, you would get sodium hydroxide plus the hydrochloric acid and what you're going to get is water as a liquid plus the salt, which is going to be aqueous. And so if we were to do a net ionic equation of this, you would see that you get the sodium plus the hydroxide plus the hydrogen and the chloride, which are going to produce the water, which is liquid, so we're not going to separate that, plus the sodium plus the chloride. And so we're going to cancel the chloride and the sodium because they're the aqueous salt, right? We cancel them from, remember when we did net ionic equations. And what we're left with is going to be the hydroxide plus the hydrogens and they come together to make water. Now, because it's a 1-to-1 ratio in this equation, that neutralizes any pH, which we're going to talk about later, but I know you've heard of, okay? So the pH of this would be neutral. As an acid and base, this would be neutral. And the reason is because all of the bases are neutralized by all of the acids. Okay, next, we're going to take a look at the Bronsted-Lowry acids and bases. So alphabetically, we're getting more complicated. So the Arrhenius acids and bases are super easy, H plus, OH minus. You know, we don't really use them anymore, except that it's understood that acids carry H pluses and OH minuses, but nothing is actually labeled as an Arrhenius acid and base. It's just understood that pH is a measurement of those H pluses, and that goes back to the Arrhenius acids and bases. All right, now before we move on, one more thing. If you were looking at hydrochloric acid and you were looking at the dissociation, a perfectly acceptable visualization of this dissociation would look like this. So the hydrogen would come over to the water and make the, this is called a hydronium ion. And I think I don't have it in my notes, so I just want to make sure, oh, I do, but I just wanted to make sure I get it in there, so that's why I'm putting it in there. It is interchangeable between the H+. So no matter what you write, it is acceptable on the AP exam. Whether you write this equation or this equation as a dissociation, it is acceptable. H3O plus and H plus are interchangeable, as long as they fit into the equation, okay? So it might say, like, show the dissociation of the acid. If you dissociate the acid without water plugged in there, that is fine. You can just dissociate the acid alone, okay? All right, let's keep going. Bronsted-Lowry. So Bronsted-Lowry is interesting. The acid is considered to be a proton donor. So proton being H plus ion, donor, and then the base is considered to be a proton, H plus ion, acceptor. So one might say, oh, well, that's kind of the same. Sometimes they're the same, sometimes they're not, but the point is that in the end, it looks different. So the idea here is, and I want to be clear, the idea here is once an acid gives up its proton, it becomes a base because it now can accept a proton back. And this is very important on the AP exam. Very important. Okay, let's take a look. So I'm going to look at that hydrochloric acid equation. And I'm going to add the water in. Okay, and then I'm going to dissociate it. So on the other side, I'm going to use the hydronium ion. Because in this case, H3O plus. In this case, that's going to be important. Plus, I'm going to get that Cl minus. All right? Now, the reason this is important is because this hydrochloric acid is the acid, and the reason is because it donates the proton to the water. So that makes the water the base. Why? Because the acid donates the proton to the water. So now the water is acting as a base. And so all of a sudden, now something important is happening here. It's relative. It's against the other thing. Water, which is neutral, is now acting as a base. It's not giving up an OH minus. It's accepting a proton. And so it is acting as a base next to the hydrochloric acid. Is it giving up an OH minus? No, it's not. All right, it's not. But it's acting as a base. And so we can look at others where we can look at a base. So here's an NH3 plus AQ, right? Plus water, which is liquid. And on the other side of this equation, we get NH4 plus, aqueous, plus OH minus, aqueous. Uh-oh. All right, so now the water donated protons to here, to the ammonia. So now the ammonia acted as a base. Why? Because it accepted the protons, and the water now acted as an acid. because it gave up a proton. So this relationship is extremely important, the relationship between the acid and base. And because now we also have to label the other side of this equation, all right? And so we're going to do that. But before we do that, we want to talk about the fact that water has the ability to act as both acid and base. It is called amphoteric. It could be an acid or a base. And water is just one of them. So, or you could look at something like H2PO4 2-. So in this case, this is H3PO4, which has given up one hydrogen, and it has another hydrogen to give up. It has another hydrogen to give up. So it can either act as an acid, a very weak acid, but an acid, and give up another hydrogen, or it can accept a hydrogen. This is amphoteric. Okay? All right, now let's move back up to our hydrochloric acid reaction. And I want to show you something. In Bronsted-Lowry equations, they have, on the reactant side, they always have an acid and base. And then on the other side, they have a conjugate acid and a conjugate base. And this is what happens after the reaction has taken place. So this base becomes the conjugate acid. Why? Well, now it's an acid, isn't it? And the reason that it's a conjugate acid is because it can now give off an H+. And then it would be water. See that? So it was a base to begin with because it was going to accept the proton, and then it became a conjugate acid because it now has an extra proton to give off. Meanwhile, the acid over here, that is going to become a conjugate base. Because it started as an acid where it had a proton that it was going to give off easily. And then it became this base where it can now accept a proton. And by definition, that is the definition of the Bronsted-Lowry acid and base. Will you donate a proton or will you accept a proton? Now, not everything is an acid or base in Bronsted-Lowry's view, but if you are, you're either going to accept or you're going to donate. And if you accept, you then become a conjugate acid. And if you donate, you then become the conjugate base. Because then you can accept and go back to be an acid. Now, the more interesting thing about this, so let's put that down, all right? So, in other words, right, an acid donates proton and becomes the conjugate base. A base accepts the proton and becomes the conjugate acid. So there is the question on the exam, multiple choice, sorry, on the exam, multiple choice question. Which of the following, for example, which of the following of these equations is labeled correctly? Or which of the following is the conjugate base for hydrochloric acid? And then there's an equation there, right? Or which of, do you see what I'm saying? So it's a multiple choice question. And then knowledge from what I'm about to tell you is used on the test in an acid-based question. But there's always a multiple choice question on Bronsted-Lowry's. Okay? All right, now, really important here is strong acids form weak conjugate bases, and I want to talk about that for a minute. And we're going to go over this again. Like, we'll talk about this again later with numbers. But I want to just talk about the concept of this for a minute, because it's going, as we go through the acids and bases, and I'm going to mention it again and again, you're going to kind of go, oh, yeah, that makes sense. Oh, yeah, that does make sense. Oh, yeah. And it's going to start to gel. And then by the time we get to the numbers, it's all going to be like, yeah, of course. Yeah, okay, plug this in. Oh, I don't even have to think about, like, how did you know that? It's all going to make sense, all right? So strong acids. So here we go. Remember that we're looking at a reaction being driven in one direction or another. Okay? So this reaction actually is driven hardcore. 100%. Hydrochloric acid is a super strong acid. So this reaction has a super high products on top. Processing time. Products on top. Super high K. Products on top. Okay, good. Super driven over to the products, okay? All right. So it goes right over here. And so here we are, we're sitting over here, we have an hydrogen ions floating around, and we have chloride ions floating around. Why don't they connect back together? Why is this such a weak base that it doesn't accept the protons? Right? Remember, bases, a proton acceptor. Why doesn't it accept a proton and drive back in the other direction? Well, what happens when it gets back over there? Bump. Right? So every time this chloride starts to hook up with a hydrogen ion, what happens? Bump. You with me? This is a hugely strong acid. There is no chance that this chloride is going to head back in that direction. Yeah. Page 751. The list. You got to copy it down and you got to memorize it. Literally, you can figure out a way to memorize it. In fact, there was a huge argument on the Facebook page last year after the test because they didn't use a common strong acid. They used one that wasn't so common. And so there was a huge argument that schools like in Florida, where we don't have as many labs and we don't have as much, not as much attention, and kids don't have like a pre-AP class before they're in AP and blah, 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 blah. And the kids up north who are so better versed with all of this stuff, they were all like, well, we thought it was fair. I mean, it was kind of obscure. And people from Alabama were chiming in and saying, yeah, your kids are a little bit higher level than ours. And if they were testing for whether they knew strong or weak acids, that's one thing. But they weren't. They were testing to see if they knew Bronsted-Lowry. And if that's the case, why don't you just give an acid that we know is strong or weak? Which is absolutely true. Don't test with things that are obscure pieces of knowledge. If you're testing for this, then just give us an acid that's strong or weak. So you have to memorize it. So the list, and we'll put it on the thing and we'll work with it, and you have a lot of things to work with, but there's a list of strong or weak on page 751 that you'll work with today. I would write them down on a piece of paper so you don't have to keep flipping in the book. All right, and it's got bases and acids, and then as we go, you'll get better and better at it, and then we'll start playing games with it in May. In April, we'll start playing games with them and matching games and stuff like that. so that you have them. All right. But strong acids, so that's the thing. The stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. So if you know that this is a strong or weak base, then you'll know whether this is a strong or weak conjugate acid. Okay, moving on. Okay, so when we talk about the K, the dissociation constant, so now, like, we're out of that. We're not going to do Lewis acids and bases till later, all right? So that was like the Bronsted-Lowry. We're sort of still in Bronsted-Lowry, but not directly, but we're only using the Bronsted-Lowry and the Arrhenius definitions now, okay? So this is the acid, it is Ka for acid. So you can imagine there's also a Kb, right? Okay. And so if we are looking at HCl, right, which is going to go like this, and it's going to go H plus Cl minus, right? Okay, then my Ka would be right? Now, here are two things. Here we go. HCl is a strong acid. Strong acids dissociate 100%. So therefore, we don't need that because there is none left. I'm going to repeat that. Strong acids dissociate 100%. And so therefore, the equation actually looks like this. With only one arrow. Because there is nothing left when it dissociates. Whatever the molarity that you start with, think about your ice tables, whatever the molarity that you start with is the molarity of the hydrogens and the molarity of the chlorides at the end, and there's nothing left of your initial HCl. It's a 100% dissociation. Okay, 100%. And this comes up all the time because if you're doing a pH, you have to calculate the concentration of the H+, but you don't have to calculate it in your strong acids. It's the same as your initial concentration. Okay, so we only have to calculate them for weak acids. The stronger the acid, the weaker the conjugate base. So, and the smaller the Ka, the weaker the acid. So let's think about that. The smaller the Ka, the lower the product, right? The lower the product. So therefore, the less the percentage of ionization, the less it's moving over to the right. All right? And so that's why it's weaker, because the Ka of the stronger acids are shifting all the way to the left, to the right. Is everybody like starting to put all this together? So this chapter is, there's a lot of information, but it all kind of like pulls together a bunch of things that we've learned so far. Okay, so now we're going to take a little break, and we're going to talk about the ionization of water. Okay? So we've done acids, right? And so this is Kw, the ionization of water. Now remember, water is hydrogen and hydroxide, right? So the Kw is equal to the concentration of H plus times the concentration of OH minus. Oh, that makes sense, right? Because water is going to always, by the way, always dissociating back and forth. It's always doing that. It's always going like this. But the thing is that it's equal parts hydrogen and equal parts hydroxide, so that is fine, that it is doing that, okay? It is okay. So the Kw is equal to 1.0 times 10 to the minus 14th at 25 degrees Celsius. And as always, if I were to raise that temperature, then that would change the Kw. All right? But this is the one that we always use. So if I were to do a little algebra on this, a little algebra, what I would find is the concentration of H plus is equal to the concentration of OH minus, right? Because they're equal. Okay? Which is equal to the square root of Kw. Well, you see this? Because they're squared, right? Because it's x times x, right? Which is equal to 1.0 times 10 to the minus 7th at 25 degrees Celsius. So in a basic solution, then, the concentration of OH minus is going to be greater than 1.0 times 10 to the minus 7 because it's basic. The concentration in an acidic solution the concentration of H plus is going to be greater than 1.0 times 10 to the minus 7. Now remember, they're multiplied together here. So if the concentration of the H plus is greater than 1.0 times 10 to the minus 7, this one is less than that. Because they equal 1.0 times 10 to the minus 14. And in a neutral solution, the concentration of the H plus and the concentration of the OH minus is equal to 1.0 times 10 to the minus 7. So I've said this kind of a few times now, right? Okay, well, let's start talking about pH. Okay? Nope. I think that's enough. I think that was a lot. But it wasn't a lot like, you know, it wasn't a whole lot of hard stuff, right? It was okay. All right. So homework is already posted, and you can get started. The book's over there. You have about 15 minutes. All right? Yeah, it's not like, you know, because we've already done a lot of it, so, yeah, all right? Okay.